Welcome to the first semester of Technical Physics, EGG131, College of Southern Nevada. Technical Physics, first semester, is really made up of three major areas: mechanics, thermodynamics, and vibrations in waves. In the mechanics sections, you can see we've got 9 chapters or 9 areas that we'll look at, and those areas are really the building blocks for the rest of the semester. With each chapter, we learn a little more about the units and the measures and the concepts that are involved in technical physics. So the first thing we need to do in looking at technical physics is understand measurements and problem solving. So in this first section, chapter 1, we're going to concentrate on measurements and problem solving and those things that become the fundamental building blocks for technical physics. In the areas that we're going to look at, why and how we measure, the units that we need to understand and know for measure, something about the metric system, unit analysis, unit conversions, significant figures. Significant figures is an area where a lot of students have trouble understanding what the values are that were given to you as the initial data and the solutions that you come up with in your analysis. You always have to make sure that your significant figures match. Otherwise, you'll be overstating the solutions to your data. And then finally, problem solving. Problem solving is a methodical process for solving any type of problem in the technical world, whether it's physics, engineering, or any area of science. So the goal of physics is to provide an understanding of nature by developing theories based on experience. And so through experimentation and through collecting data and understanding how to handle it and how to process it, we get a better understanding of nature. The theories are usually then expressed in some mathematical form. In physics, you're going to see that there is a strong use of math. Some students are quite surprised at how much math is required in a physics course. It's possible to understand the behavior of a variety of physical systems with a limited number of fundamental laws. The nice thing about this is you can take those fundamental laws and they become the building blocks for the tools that you need later as you progress through your learning of physics. So the following chapters then will be concerned with the laws of physics. Why and how do we measure? We need a clear definition of basic quantities so that we can apply them to the laws. The physical quantities, as we will see them develop, force, velocity, volume, and acceleration, can be described in terms of more fundamental quantities. These fundamental quantities are the units of length, the units of mass, and the units of time. With length, we know that we have different ways of measuring our lengths, whether it's the British system or the metric system. In mass, we can deal with pounds or we can deal with grams. And with time, it just depends on how small an increment we want. We can do seconds, minutes, hours, days, months, weeks, years, or we can go the other way into fractions of units of time: milliseconds, microseconds, nanoseconds. Force, velocity, volume, and acceleration then become derived from those 3 fundamental units. As we get into this, you're going to see that those 4 examples, force, velocity, volume, and acceleration, have fundamental quantities from length, mass, and time associated with them. For instance, velocity is length per unit of time, whether that's meters per second or miles per hour. Force is equal to mass times acceleration, which can be broken down into kilograms times meters per second squared. And so with each unit that we come across and we build, we will see that we are adding to typically some unit of time associated or some unit of mass associated to come up with a new unit which is derived. The SI units, or the Systems International units, then, for length, mass, and time, are right now measured in these three areas, units of times. But be aware that those units and those measures vary in time, over time, based upon our ability to become more and more precise in our measures. Length, then, is the distance traveled by light in a vacuum during a time interval of 1/299 millionths, 792 thousandths, 458 hundredths of a second. Okay, so that's a pretty exacting measure for length. The established speed of light then from that is 299,792,454, or approximately 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second is pretty much our standard unit that we will use in our calculations. The thing that we have to be aware of is that this is in meters. Sometimes the measure is in centimeters. Sometimes it's in millimeters. Sometimes it's in kilometers. You just have to be careful when you select your units. Mass has a unit of kilogram. A specific platinum iridium cylinder kept at the International Bureau of Weights and Measures in France becomes our standard for which we identify a measure in grams. Thing that we always have to remember is that mass and weight are not the same thing. Mass is the fundamental unit. Weight has a unit associated with it that you have to look at in terms of gravity. And if you will constantly think about gravity giving mass weight, you will differentiate between those two units. And time, typically the second, is defined as 9,192,631,700 times the period of oscillation of radiation of a cesium atom. So you can see by these measures, they're pretty exacting, and these measures then help establish the standard for which we use. Mass then is a quantity used to measure the resistance to a change in a state of motion of an object. It's difficult to cause a change of state of motion of an object with a large mass than it is with a small mass. So think in terms of a huge boulder or a ping pong ball. A huge boulder has so much mass that it's very difficult to change its state of motion. If it's in rest, trying to get it to move is difficult. If it's moving, getting it to stop is equally as difficult. Mass then becomes a measure of inertia. The inertia is the tendency of an object to continue in its original motion. We'll later explore momentum and see that inertia is not the same as momentum. In looking at an example here of a GPS global positioning system, we can find a location by triangulation. Suppose you're at a big university and you want to find your location on a campus map. You know that you're 1 block from the bell tower. Draw a circle with a 1 block radius with the bell tower at the center. So you're somewhere inside of that circle. You also know that you're 2 blocks away from the gym. Draw a circle with a 2 block radius with the gym at the center. You are either now from the diagram at point A or point B. You also know that you're 3 blocks from the college gate. Draw a circle with a 3 block radius with the college gate at the center. You know that you are now at point 1 because the 3 circles intersect there. So that's a fundamental way of measuring using something called triangulation. The same idea works for spheres. In this case, looking at the GPS satellite system, you can see that with just 3 satellites, your location can be determined. It may not be very accurate, but it has a pretty good probability of the area where you are located. Other systems of units, the Gaussian and the British systems. The Gaussian or the CGS system uses units of measures of centimeters, grams, and seconds as length, mass, and time. In the British engineering system, or the conventional system, we use the foot, a slug, and a second. So you can see that we vary between several units of measures and systems of units in order to come up with commonly used units. A very important measure for understanding the size of a unit is typically used in scientific and engineering applications. We use the metric prefixes, or those that relate directly to powers of 10. If we look at the uppermost measures on this chart, 10 to the 18th power, that's 10 times itself, 18 times, we come up with a prefix we call exa. If we look at 10 times itself 12 times, we have a unit of tera. If we go to the opposite extremes, 10 times itself to the minus 18th times, we have a unit of atto. What happens is you will become very familiar with using these prefixes as shortcut measures for doing calculations and analysis. For example, 10 to the minus 3 meters is equal to 1 millimeter. 10 to the third meters is 1 kilometer. 10 to the third grams is 1 kilogram, or 1,000 grams, and 10 to the 6th volts is equal to 1 megavolt, or 1 million volts. Okay, so it's easier to use the metric than it is to use numbers with leading and following zeros that get very, very large and cumbersome. In the next section, then, we'll take a look at the building blocks of matter.